Welcome back, everyone. So, in the previous section, we looked at a variety of transformations available for data augmentation, things like rotation, flip, etc., and also the normalization. Now, what we are going to do is design the CNN architecture. And for that, I'll start with importing some of the important libraries, and I'll do some, bit of copy paste here. I'll copy this entire cell. There you go. And make some changes here. That is, I want the transforms and also the models. Okay. And then I'll want to suppress the warning as well. And that is also, I'm going to put that this entire thing in that same cell. Yeah. Again, we have gone through the discussion of all of them. But just as a revision, this is Torch, the main PyTorch library. This torch.nn, it contains the module for building neural network. This torch.nn.functional, it provides function for common neural network operations like activation functions and pooling and etc. Then we have to data loader that is going to load the data in batches. This here, the transforms and the model, they provide some common image transformation and also provide pre-trained models that we are going to be using. Then we have the three libraries, pandas from for using the data frame, NumPy, that is numerical Python to deal with the numbers and NumPy arrays. Then we have the the data visualization library, that is Matplotlib. And lastly, we have this OS image and display. Just this is going to deal with the file path and so on. Now I'm going to import, not import, rather use a transform here. And we have seen that how to apply all the transformation in one go over here, right? So I'll copy this entire thing. Okay. And I'm going to create two instances of the same. One is the train transformation. All right. And that is going to have the random rotation of 10 degree, not 30 degree. It is going to have the random flip, the center crop of 224, then 2 tensor, and resize of just 224. Right. So I'm going to resize the shortest side to 224 pixels. And then I'll also normalize this. So I'll say transforms dot normalize, and it's taking in a list of the numbers that we have already created here. Again, you can copy this as it is and paste it. All right. Then similarly, I'll do for the test transformation as well. That is going to have the test transform, and that's going to be, well, in test transformation we don't have to perform any flip here because we are not feeding this data to our model. So we don't have to perform, we don't basically have to augment the image. We just have to make it ready for the testing, right, to test our model. So I'm going to remove the rotation and flip, both of them, and I'll be left with center crop and resize and the two tensor and the normalize here as well. Let us run that. Okay, now let us prepare the train and test set here. And for that, again, I'm going to copy the file path from here because we want to read that. And that is here. Okay. Um, well, never mind. I'll just copy this path here, and the rest of the things I'll do it myself. So I'll see, first of all, the train data is going to be equal to datasets dot image folder os dot path dot join and its root and train. Okay, then transform here is equal to train transform is this. So this is the transformation that I'm going to apply on this. And similarly, I'll copy this and I'll call this not as a path, but root here, right? Because that is the variable that I'm taking. And then you'll have the test data similarly. This is test data. And this is test here as well. All right. And transformation similarly is going to be the test transformation. Great. Now, the once you have grabbed the data, we want to feed the model, feed this data to the model in batches. And for that, we want to create the batch sizes. So I will create data loader that is going to take the train data, and that is going to have all the images, right? And you can just navigate through and see how many images are there. There are about 25,000 images, but in those images I would put a batch size of 10, and I'll also shuffle them, right? So what you're doing is of all the 25,000 images, I'm going to pick just 10 images out of random, right? And then I'll shuffle the remaining images. Why we are doing the shuffle? Because every time we pick 10 images, I'm going to shuffle it so that I'll choose some random images. Now, granted that this will have its own challenges, because every time we are doing the shuffling, we are going to pick a different set of image, and thereby your model performance will be different as well. So if you want to reproduce your result, what you can do is you can set a seed here. Now, if you're not aware of the seed, this is going to enable you to reproduce the result anywhere in the world, anytime in the world, and you can you'll get the same result, right? No matter which system you are running on, you'll get the same result again and again. So to reproduce the result, we'll set some manual seed. Again, you can choose any kind of reasonable number, any reasonable 2-digit number to get that you can put over here. And I have the test loader equal to data loader and test data, comma, batch size equal to 10, and shuffle equal to true. All right. Then once you have this train data, you will see, okay, I'm getting an error here because I've not imported data sets actually. So you'll have to put data sets here as a module and run everything. Okay, anyhow, now it is working fine. Anyhow, the point is you can see that if you take this train data here, you'll see that it is a bunch of dictionary, right? Not a dictionary kind of thing, but the point is you're getting all these things here. Now, what I want to do here is I just want to grab the classes. So I'll take train data and say classes here. And that's going to tell me that what are the classes inside that training data. Okay. Now we've already seen this. That is this is over here. You can see that I have in training data, we have cats and dog. Similarly, so these are the two classes that we have, that is cat and dog. And this I'm going to assign to the classes or class names. Okay. Now let us see how many of them are training data and how many of them are testing data. So for that, I'll say length of train data. There are 18,000 images. Similarly, length of test data, there are 6,000 images. Okay, so this is what I'm having. Now let us try to display some of the images. Already we have seen how to display them, but what I'm going to do is I'm going to display the batch of the images. You can see here I've already said that we are going to feed our model, feed the data into our model in a batch size of 10. So let us display a single batch here. So for that I will say display a batch of images, and I'm going to say that for every image or images, comma labels in train loader. I'll say just break. Why break? Because I'm just grabbing, images over the label. And I'll say that print that label is labels dot numpy, and this will show you that what is the label over here. Now, what is the 0 and 1? It will be clear shortly, but it is, for example, 0 is going to be cat and 1 is going to be dog, or vice versa, right? So we have the label, and I'm going to print the class here. So class here as well, and that's going to be asterisk np dot array, and you're going to convert that class names that you have taken for every index in, sorry, for every I in labels. And just close this square bracket, close this parenthesis, and close this parenthesis as well. If you run that, you can see, yeah, 1 is for dog and 0 is for cat. All right. Okay. Now what I'm going to do is I'm going to make this IM equal to make grid. Maybe we'll have to import this as well because I've not imported it apparently. So for that, you'll have to go back and in utils, you'll say from torch vision import, sorry, torch vision dot utils, remove this, torch vision dot utils, I'll import make grid. Run that, run everything, come back, and here you'll see that in make grid, I'm going to pass in the images and number of row as 5. You'll see why I put 5 here, but this is what I have. Now I'm going to copy one more thing that is going to, do a inverse normalization, because so far we have normalized the image, but if you want to display the image, as I've said in the, previous notebook as well, that is, we have to do the inverse normalization. So I'll just copy this entire thing. Okay. And come here, paste, and just pass in this thing as well. This two things over here, and that should give me some cats and dogs images. Now, every time you run this, it's going to grab a different set of 10 images. Why 10 again? Because that is the batch size. It is going to grab a different set of that batch, and it is going to display those images. Okay, so you can see here, every time I'm running this, is going to grab a certain set of images, their label, their classes, and the image itself. This is just for demonstration. Okay, but now let us move forward and start by using a model, or should I say designing a model. Now, when you are designing a model, one thing that you have to understand, if you're not aware of it already, that the designing architecture takes like months and years sometimes, right? So obviously this video cannot be a month long or a year long. What I'm going to do is I'm going to since it's a project that I've done earlier, and it's a very well established project as well, what we are going to do here is we are going to take the established set of the architecture, right? But again, the thing that I'm going to enter here, it has been found empirically after a bunch of bunch of experiment and things like that, and they have come up to this architecture. But let us design that architecture here. I'll say class, I'll say convolutional network, and it's going to inherit nn dot module. I'll say def underscore underscore init underscore underscore self. I'll say super dot underscore underscore init underscore underscore. Then I'll say self dot convolutional one equal to nn dot convolutional 2D here is 3631. Now, what is this? Well, let me start from the very beginning. What we have done here, we have defined a class that inherits an n dot module, the base class for all the neural network modules in PyTorch. Then we have created the constructor for the network. Then we have called the constructor of the parent class, that is nn dot module. Then this one, it defines the 2D convolutional layer. It takes three input for RGB image, three channels for thereby three input channels, and then output is six, that is six feature map. And it uses a 3 by 3 kernel, right? And it has a stride of one. Now, everything that I'm saying here, I know it is, if you're not aware of CNN, well, you have to go through the theory for that. But you can see here the first argument is input channel, second argument is output channel, kernel size and stride, then padding, which I'm not given, but the default padding is 0, and dilation is 1, and so on and so forth. By the way, if you do a shift tab here, you can see this options over here. This is a help section of this particular thing. Now, anyway, this is what I have. Now, I'm going to create similarly the conventional layer 2. So I'll say conventional 2 equal to nn dot convolutional 2D pass in 6, 16, 3, and 1. Right? And I'll say self dot fc1 equal to nn dot linear and pass in 54 into 54 into 16. Right. Don't worry, I'll explain this 16 as well, but let me just finish this. Self dot fc2 equal to nn dot linear pass in 120 by 84, and then self dot fc3 equal to nn dot linear. This is 84 comma 2. Okay, so first one, it defines the first fully connected linear layer. The input feature 54 by 54 by 16, it comes from flattening out the output of the last pooling layer. And it outputs 120 feature that goes to the next layer here, that is 122. And that is going to output 84 layer, neurons, and that is going to feed to the next connected layer, right? So it takes 84 input and outputs 2 feature corresponding to the 2 classes, that is cat and dog, for binary classification. Okay, so this is what we have. Great. Now let us see again how this 54 is coming up. If it is not already clear, well, there is a formula that is going to say you have 224 pixel minus 2. You take this 2 here and divide by 2. Then you take this entire thing again. Then you do a minus 2 here again. Then you take this entire thing again and you perform a division again. If you do that, you will get 54.5, which rounds to 54 pixels per side. And that is how we have gotten this 54 here. Okay. Again, theory should clear that. All right. Anyway, then I'll say def forward self x, and then I'll say x is equal to f dot ReLU activation function is going to take self dot convolution 1 x, then x equal to f dot max pool 2D pass in x comma 2 comma 2 is this, then x equal to f dot ReLU pass in self dot convolutional 2 and x here. Then I'll say x equal to f dot max pool 2d x comma 2 comma 2. Don't worry, I'll explain this here as well. Then I'll say x equal to x dot view. You are going to flatten this out and just reduce this to 54 into 54 into 16. And x equal to, you are going to take self dot fc1, pass in x, and you are going to pass this entire thing in f dot relu. That's what you have. Then x equal to self dot fc2, x here is this, and you'll get f dot relu as well. Okay, then x equal to self dot fc3 x, and that at the end will return f dot log softmax, pass in x comma dimension 1. There we go. This is the class that I have defined. Again, the remaining part is we have creating this forward pass of the network, specifying how input x is going to process through the layer. Then this one here, it applies the first convolutional layer followed by a ReLU activation function. This, it applies a 2 by 2 max pooling layer with a stride of 2. Then this applies a second convolutional layer followed by a ReLU function. Then this again applies the max pooling. Again, same idea, 2 by 2 max pooling layer with a stride of 2. Then we are flattening this out, flattening out the output of the last pooling layer into 1D vector. The -1 means PyTorch will infer the batch size, and 54 by 54 by 16 is calculated number of feature from the convolution part, which we have already discussed. Then this one, it applies the first fully connected layer followed by a ReLU function. This one, it applies the second fully connected layer followed by a ReLU function. This one applies the final fully connected layer, but we don't put a ReLU function here because in output layer, we cannot have a ReLU function. We'll have to put a log softmax activation function to the output. Log softmax is often used with NN, negative log likelihood loss, or implicitly NN dot entropy, cross entropy loss as well, which combines basically log softmax and NN loss here. So anyway, this is what we have done. That is, we have created this function. Now what we have to do is we have to look for GPUs. Now this is the part that all of us will again vary. So I'll say if torch dot backends dot MPS is available, then you're going to say device is equal to torch dot device. This is equal to torch dot device MPS. Okay. Now this is only valid if you're on Mac, right? If you're on MacBook, you can use this. This is using MPS device, that is Apple Silicon GPU. Elif, you'll say torch.CUDA. So if you have inbuilt, GPUs with you, you can use this one then. That is, you'll say device equal to torch.device CUDA. Else, I'll say device is equal to torch.device pass in CPU. So if you're not having the GPUs, then you can use the traditional CPU, that is your normal processing system, and just check which device you're on by passing in this device. So I'm on MacBook, so I have MPS here. All right, so that's what you have. Okay, so this code is again very important if you're on GPU. But if you're not on GPU, then if you know that you are on CPU only, you can skip this part, right? It's on you, depends on what system you're using and all that. But now let us instantiate the model. instantiate the model, and also define the loss and optimization functions. So I'll say CNN, and here also you can set a seed if you wish to. So I'll say manual seed and pass in 50, for example. And I'll say CNN model is equal to convolutional, the instance, the class that you have created. Just a second. The name of this is convolutional network. So this is convolutional network here is this. Then you take the criterion equal to nn dot cross entropy loss. Then I'll say optimizer equal to torch dot optim dot Adam optimizer I'll be using. Again, adaptive stands for adaptive learning. If you're not aware, that is the optimization algorithm. So it takes the model's algorithm, model's parameter by, and you can get that by you saying CNN model dot parameters here, and then learning rate equal to 0.001. Okay. And if you just pass in CNN model here, you'll get this. Great. Now look at the trainable parameters. Yeah. So I'll say that def count parameters here we'll say that, never mind, what I'll do is you can just call this params here and say p dot uh number of element for every p in that model. Which model? The CNN model dot parameters if p dot requires grad. And then I'll say for every item in params, I'll say print f literal as that item greater than 8. If you run that, I'll got a problem here because here you'll have to pass in, you have to close this bracket here basically. If you run that, one more error because has no attributes parameter. There's a spelling mistake, so fix that. There you go. One more error here. Well, we'll have p dot requires grad. There should not be any parentheses here. Now, there we go. So this is the number of parameter that we are getting. Okay. Every time we are getting this, we are having this parameter. Now, what you can do is if you check the params here, by the way, these are all the numbers, right? So if you take this and say that I want the summation of this is the total number of parameter. That is about, I don't know what this number is, but this is what you're having. Okay. So it tells you the sum of all the trainable parameter. Great. So much, so far so good, but really the fun comes when we have to actually train the model. So let us do that. I'll say this is train the model. All right. So I'll say import time. Why I'm importing time here? Because I want to keep track of how much time we have spent training the model. So I'll say time dot time as this, and I'll say start time is equal to this. Then you'll have to set some epoch, and this is the point that it depends on you how much time that you have. I recommend that you should at least train for 20 epoch, but again, it is going to take some time, right? Just be mindful here. If you're on normal CPU, if you're coding out on CPU, I suggest that you can put maybe about 5. That should be enough. But if you're on GPU, especially on MPS, you can definitely go for 20, right? And that should be enough in my opinion. But you can always go for a larger number as well. The more number of epoch you train your model on, the better it is. But do not kind of overtrain. Do not overfit your model. That is also important. However, for now, I'm going to create a variable. I'll say maximum training batch is equal to 800, and max test batch is, let us say, 300. Okay, so basically, we are these two things. We have created this variable to limit the number of training batches and testing batches for epoch to 800, and we are limiting the testing batches for evaluation to 300. Again, it will make sense later on, but for now, let us create some more things. I'll create some empty list. One is to store the trainable losses, or should I say training losses. Then I'll say test losses is equal to empty list. Then I'll say train correct values is empty list. Then test correct here as well, that I'm going to store later on, is going to be this empty list as well. Then I'm going to say that for every epoch in range, the epochs that you have defined, whether it is 25, whatever, I want to go through, I want to repeat this thing for every epoch. What we have to repeat, basically, first of all, and this is going to be a lengthy code here, so please be mindful. But the point is, I'll say that if, well, never mind the if, I'll say training correct is equal to 0. I'm setting variable again. And similarly, I'll have test correct values as 0 as well. So basically what I'm going to do is for every batch, I'm going to understand, or I'm trying to make sure that what is the predicted value and what is the correct value. If predicted value and the corrected value are same, then basically we have got our prediction right. We are going to put that number here. For example, for out of a batch of 10, I'm getting 8 right? I'm getting 8 predictions right. So I'll put that 8 over here. Okay, and I'm going to do that for all the batches here. But anyway, let us first say B for batch and X train, comma Y train in enumerate train loader. Don't run this, press enter. Then limit the number of batches. So I'll say if B is equal to the maximum train batch, I want you to break out the loop. Okay, and just put b equal to b plus 1. So take the next batch basically, right? Then I want you to apply the model. Okay, for that you'll say ypred equal to CNN model and pass in xtrain here. Okay, and I'll say loss equal to criterion and pass in ypred and ytrain. All right, and then we'll say get the prediction equal to tosh.max as this, and you'll say ypred dot data comma 1 and 1 here. Okay, so basically I'm getting the prediction, then I'm getting the data. Now that what we have done here basically is we are getting the class with highest probability from the model's output. That is what this thing is all about. So that we are the one with the maximum probability will be my predicted value. right? For example, if there's a prediction of a cat image, or sorry, rather, image being of a cat image, then if that probability is about 80%, then the predicted value would be the cat. Okay. Similarly, if there's a 30% probability that it's a cat image, that means there's a 70% probability of it being a dog image. So I'll say, the predicted image is of a dog, and so on and so forth. So you'll have the predicted value, and similarly, you'll get the losses here as well. So what is the losses here? We have already defined that. That is criterion. Pass in the pred value. Okay. And in fact, oh, we have already done that. I'm sorry. We are here getting the predicted value. I'll take this predicted value and just check whether this predicted value is equal to y train, right? And in a batch of 10, there will be bunch of predicted values, right? So out of 10, how many of them is true? For all the trues, I'll get the sum of it. For example, 8 of them are true. That is, for 8 of them, the predicted value on the label is same. Thereby, 8 would be the summation, and that is the value of the correct value for that particular batch. That is, the correct predictions for that particular batch is, for example, 8. Then I'll say train correct plus equal to batch correct. And then I'll say update the parameters. I'll say optimizers dot zero grad. And I'll say loss dot backward. This back propagation step. And this is optimizer dot step. And I'll say you print the and trim results. I'll say if which batch percent 200 is 0. I'll say print f literal epoch is to 2. Then the batch is then this is curly braces 10 into b 6, then divided by 8000, and loss would be loss dot item here. All right. Then we have the accuracy that you have to get, and accuracy would be the training accuracy. Sorry, training correct dot item. That's into 100 divided by 10 into p. And you can do a copy paste of this, right? So you, again, this is just for demonstration. You don't actually have to write this, but it is completely optional, this particular code, line of code. So you can basically skip this two part. Okay, not needed, but it is important to get the result. And you can do a copy paste here as well, no issues. Anyway, so this is what you have. And then once you have basically gotten all the predicted value and gotten all the training correct value for this particular batch, what you have to do is you have to take that train losses. This is the empty list. So you get that train losses and append it. For that particular epoch, what is the loss? Similarly, you'll get the train correct and append it. Pass in the correct value. That is train correct. Okay. Now let us run the same thing for the test batches. So I'll say with torch.noGrad. I'll say for every batch B, comma, X test, comma, Y test, and enumerate test loader. I'll say if batch B is max test batch, then you break out of the loop, right? Same thing, just like what we have done in the training set, we are doing in the testing set as well. Then I'm going to apply the model and assign that to validation. So I'll say CNN model and pass in X test here. All right, then I'll say tally the number. Again, the same thing that we have done here, I'm going to do that over here as well. So I'll say the predicted value is equal to torch.max and pass in y validation dot data comma 1, pass in 1 here. Then you'll say test correct is equal to plus equal to predicted equal to y test dot summation. Okay. And at the end, I want to assign the loss to the criterion, that is y validation, comma, y test. This is the loss in the testing set, right? And so I'll say test losses dot append this loss here and test correct as append here, and that would be test correct. At the end, I want to just know the duration of the thing. So quite a code here, but let us, print the duration. Hopefully I'll get this right. If there are some error, we'll have to fix that. I'll put some, n \n. I'll say duration is time curly braces time dot time minus start time. Okay, and seconds. All right, now let us run this. This is going to be quite a code. And to be honest with you, if you are running for 20 epoch, even if you're on Mac, I'm on MacBook Air, but is going to, and on M2 chip, by the way, but this is going to take quite a time, right? It's going to take about half an hour in on my system, I think. Again, I can only suspect that. So what I'm going to do is I'm going to stop this video here. And in the next video, I'll show you the result of this and I'll also give you a walkthrough of this entire code. So stay tuned. We'll see in the, I'll see you again in the next video, right? Let me run this and let us check whether it is working or not. There we go. So we have not, epochs is the problem. So you can just put a S here. That should solve. Again, y train is not defined. So let us see what is the issue here again. Y train is, yeah, this should be small case y. Run that. Should work. Let us wait for this because it might take, a few seconds to get the first result. There we go. It's working fine, right? So I'll let it run. And when I come back in the next video, we'll discuss it further.